Most often, our primary interest in models like these is interpreting the value of the coefficients. What does the model tell us about the relationship between fuel economy and engine size in the context of the year in which the cars were manufactured? Let's start with the main intercept. The value is 35.276, and the units are the same as those of the response variable, miles per gallon. Recall that this is the expected fuel economy for a car from 1999 that had an engine size of 0 liters. Of course, in this case, this value has little meaning, since there is no such thing as a car with an engine size of 0 liters, but that is the literal interpretation of the role that 35.276 plays in our model. As we saw above, the coefficient on year can also be thought of as an intercept. Note here that R has chosen to report the name of the coefficient as factor year 2008. This reflects the fact that factor year was the name of the variable we gave R, and 2008 is the value of that variable that R is reporting about. This variable is identical to the newer variable that we defined in the previous set of slides. Here, R is telling us that cars manufactured in 2008 get about 1.4 miles per gallon better gas mileage than those manufactured in 1999 after controlling for engine size. This is our key finding, and I'll return to this in just a minute. How did we control for engine size? By including the displacement variable in our model, we also obtain a coefficient for engine size. This is our slope coefficient, and it tells us that each extra liter of engine size is associated with a decrease in expected fuel economy of 3.61 miles per gallon after controlling for year of manufacture. This is the negative relationship that we saw earlier. Larger engines tend to go in less fuel-efficient cars. The difference now is that we are able to estimate the size of that effect while simultaneously considering the effect of time. The interpretation of coefficients in a multiple regression model can get complicated, so let's quickly review a few common mistakes. First, there's only one slope in the parallel slopes models that we have considered thus far. Yes, there are two explanatory variables, but only the one numeric explanatory variable is associated with a slope. Later, we will consider more complex models that have more than one slope. Second, pay careful attention to the reference level of your categorical variables. Every factor in R has a reference level, which you can set, but by default, it's the first level alphabetically. Third, units are important. Every coefficient has units that relate to the units of the response variable. Intercepts are in the same units as the response variable, and slope coefficients are in the units of the response per unit of the explanatory variable. Finally, the key difference in multiple regression is that coefficients must be interpreted in the context of the other explanatory variables. The after controlling for phrasing is crucial to having a valid understanding of your model. The next set of exercises will give you some practice interpreting coefficients.